Hmm. Okay, so in last lecture we have discussed about the VI characteristics, right, of the NMOS transistor. So basically, ideal VI characteristics, if you talk very precisely. In today's lecture, we are going to discuss about the non-ideal VI effects or non-ideal VI characteristics of the NMOS transistor. Okay, so what are the non-ideal VI effects of the CMOS or NMOS transistor? Okay, that is N-type MOS transistor. Velocity saturation. Again, I will repeat. These are the non-ideal effects. Okay, these are the non-ideal effect. That means what? There is no any perfect relationship between the voltage and current, or any kind of linear relationship between voltage and current, and it is the non-ideal effects, VI characteristics. Okay, then mobility degradation, then channel length modulation, sub threshold conduction, and body effect. Okay, so along with whatever the VI characteristics that we have studied, that is the ideal one. Along with that ideal VI characteristics, NMOS transistor also exhibits these non-ideal VI effects also, right? म्हणजे जे आपण VI characteristics शिकलो, there are certain different regions. Okay, so ते तर NMOS transistor exhibit करतो. There should be a saturation region, there should be a linear region, there should be a cutoff region. Okay, fine, and you know the different conditions for that. But along with that conditions, along with that effects, NMOS transistor also exhibits these non-ideal VI effects too. Okay, which are those? Velocity saturation, mobility degradation, channel length modulation, then sub threshold conduction, and body effect. Okay, these are the non-ideal VI effects that, along with the ideal VI effect, NMOS transistor happen to exhibit this non-ideal VI effect also. Okay, there is a channel length modulation. Because of that pinch off condition, this may happen. Okay, there is a body effect, there is a sub threshold conduction. Means what? Uh, if you are expecting NMOS transistor to behave very ideally, okay, it will exhibit only the three modes of operation and region. But if you actually study, or if you actually go in detail of the working of the NMOS transistor or MOS transistor, doesn't matter whether it is NMOS or PMOS. PMOS also exhibit these effects, no problem. Okay, thing is, along with all that ideal VI effects, NMOS transistor, or simply you say MOS transistor, exhibits the non-ideal VI effects also. These are the major 5 non-ideal VI effects that every MOS transistor supposed to exhibit. Okay, in the operation condition, or in operating condition. Velocity saturation is there, mobility degradation is there, channel length modulation is there, sub threshold conduction is there, and body effect is there, right? So these are the non-ideal effects of the MOS transistor. Now, next and very important point related to the MOS transistor is a resistance estimation. Okay, what do you mean by resistance estimation? The NMOS transistor, okay, because of its geometry or because of its structure, the NMOS transistor exhibits, or NMOS transistor offer some sort of internal resistance, right? some sort of internal resistance, that to be between different terminals and different what we can say layers of the MOS transistor, right? And that total resistor is known as RDS, that is the on resistor of MOSFET, that is calculated from the drain terminal to the source terminal of MOSFET. Okay, since this total resistance is between the drain and the source terminal of the MOS transistor, right? And it is known as the on resistor or RDS on, right? This RDS on is total resistance of that MOS transistor measured between the drain and source terminal, right? So we have to estimate this RDS on or total resistance of the MOS transistor. Now, whenever there is a current flow between the N channel, right? When a gate to source voltage is applied, okay, and when the MOS transistor will behave as a resistor in a linear region only, right? In a linear region only. That means when there is a channel formation occurs, when VDS or VGS or both is greater than the threshold voltage and VGS is much greater than the VDS. This is the condition. At that point, the MOS transistor will switch into the linear region or resistive mode of operation, and it will exhibit the linear relationship. That means equivalent to the resistor. Okay. Now, because of the path from the source to drain, right? And there's that entire path, that means from source to drain, if you travel along, so that entire path is made up of series of resistances, right? And who will contribute into these resistances? Its geometrical structure, different layers, right? It is not the case that there is only N-type material and P-type. No, along with there is some sort of oxidation layer, right? SiO2 layer, some sort of what we can say terminal or the to connect that transistor to the supply, you require some sort of connection or terminal point. Then you require some sort of different oxidations layer, insulations layer. So if you consider all this structure and geometry of the MOS transistor, then when you travel along the source to drain, right, so particular that MOS transistor will exhibit some sort of series resistances, right? Some sort of series resistances. Now next thing is, what are the different series resistances that MOS transistor will exhibit? So you can look at the diagram. Okay, it's a drain to source resistors, right? Drain to source resistors, or you can say source to drain. As it's a symmetrical, you can interchange the drain and source terminal, no problem. So basically it's a R on resistor. That means the whenever MOSFET is into a linear region of operation or a resistive region of operation, then in that region MOSFET will behave as a resistor. As the characteristics you are getting is a very linear, that means current and voltage have a very linear proportion. That's why it must execute some sort of internal resistance, that to be in a series by its geometrical structure, right? And of course, one more point that you should remember, this path, whatever we are talking, the resistive part is the path where the current will flow. It is the path where current will flow from the drain to source. The current will flow from drain to source. That means by following the same path, the current will flow from drain to source. That means IDS. Okay. Now we have to know what are the different regions that came across this path, and which region offers which type of resistance. This point you have to understand. What are the its different regions and which regions offer which kind of or which resistance. So if you look at the diagram, so in all it offers six different series resistance, and that if you add all these six different resistance, then the total on resistance of the MOSFET can be calculated, right? If you add all these 6 resistance which are in series, right, and if you know the basics in series, how you are calculating the resistances, simply series. Okay, if it is in parallel, then we have a different formula, but if in series, it will be simply addition of each resistor. That's why we are selling it as a resistors are connected in series. So when you sum up all these different resistances offered between that drain to source path, and if you summarize it, or if you add up, then you will get the total resistance offered by the MOSFET, that is R on, or you can say RDS, that is between the drain to source terminal, and which is the same path where the current will also prefer to travel. Current will also prefer to travel, right? Now, what are these different regions, and each regions offers which type of resistance or which resistance? So first resistance is offered by the Rn. Okay, see, upper terminal is the source terminal, bottom terminal is the drain terminal, and we are going for the source to drain, or you can go for drain to source also, no problem. Okay, you can go for drain to source also. Then Rn is a source region's diffusion resistance. Okay, whatever the n plus region or n plus doping region we have, that particular diffusion region or the resistance offered by that diffusion region, and that is the n type. That's why we are naming it as a Rn, and it's a source region's diffusion resistance. What is Rn? Source region's diffusion resistance. Next, what is RCH? Okay, it's channel regions resistance. Okay, channel regions also offer some sort of resistance, okay, in series with the diffusion regions resistance. So RCH is the channel regions resistance. Next is a RA. What is RA? RA is a resistance of an area called the accumulation region. Okay, what is RA? Resistance offered by the area of accumulation region, right? As your accumulation region is large, then RA is also large. Okay, next resistance in series with that RA is a RZ. What is that RZ? It's a Zephyt region area resistance. Okay, or it's a resistance of an area called the Zephyt region. Okay, that is the RZ. Then you have a resistance RD, that is the drift region resistance, right? Drift region resistance, and it is the most important factor when you are talking about the high voltage MOSFET. Okay, for the low voltage MOSFET or your conventional MOSFET, you can neglect this resistor, but in case of high voltage MOSFET, you should consider or you should give importance to this drift region resistance, that is the RD. In case of low voltage MOSFET, you can ignore this term, but in case of high voltage MOSFET, it is the most important factor. Okay, or it is the most important resistance that will contribute into the overall or total MOS resistance. Okay, and the last one is a RS, that is the resistance of the substrate region. Resistance of the substrate region. So Rn, RCH, RA, RJ, RD, and RS. These are the 6 resistors, and if you add up all these 6 resistors, then you will get the total resistance of MOS transistor. That is the RDS on. Okay. So, basically, this is what about the resistance estimation. This is what about the resistance estimation. Okay, now beside the internal structure that contributes the Rn resistor, that means we have calculated this resistance based on the geometry. So the imperfect contact between the source and drain metal, or even the wiring that connects the die to the leads on the package, can also contribute to the RDS. As I told you now, that leads or the connectors, right? So that also contribute to the on resistance of the, or you can say total resistance of the MOS transistor. And so basically this RDA increases with increase in temperature, right? That means it has a what we can say positive temperature coefficient. What do you mean by positive temperature coefficient? If the resistance is increasing with the increase in temperature, then for any semiconductor device you can say it's a positive temperature coefficient, right? You can say it's a positive temperature coefficient, as the mobility of holes and electrons decreases with increase in temperature, right? When the temperature increases, its mobility decreases. Mobility decreases means what? Now the velocity is decreasing, right? Velocity is decreasing, and because of the, because and as the velocity decreasing, that means there's someone to resist that velocity, and that's why the RDS on increases along with the temperature. That means temperature increases, resistance increases, velocity or mobility of electron decreases. Resistance वाढल्यानंतर current हा कमी होणार आहे, right? And mobility of electrons is what? Major contributing factor in the current velocity or the charge velocity, right? And it is, so it has a positive temperature coefficient, right? So the same thing uh, is given here, right? Now to know the how actually aron is calculated, right? So you have another formula also to calculate the aron, that is the total resistance of the MOS transistor. Okay, so this part we will discuss in the next lecture. For today we will stop here. If you have any query or doubt, you can ask me right now.